today we will discuss about the different registers that are remaining registers of the system architecture of 80386, that are debug registers, test registers, and the last part is some few instructions. There are some system instructions. So this remaining three parts today we will see. So let's get started with the debug register. So this is a diagram or image of a debug register. Now you all know what is a debugging process. Debug means to what? To execute one instruction or one step one by one at a time, so that it will be easy for us to detect if there is any error present in the given step, or if the step is error free, it will execute smoothly. So there are certain registers, we'll see one by one. In this diagram, we can see there are total 8 debug registers, that is from DR0 to DR7. And out of that, this debug register, as it is of 80386, it is of 32 bit, that is 0 to 31. In that first 4, that is DR0, DR1, DR2 and DR3, these 4 debug registers are linear address for breakpoint, and also the breakpoints are type of 4 breakpoints. You can see DR0 is associated with linear address for breakpoint 0, DR1 is associated with linear address for breakpoint 1, DR2 is associated with linear address for breakpoint 2, and DR3 is associated with linear address for breakpoint 3. We will see one by one what exactly is a breakpoint and how it is working. Then DR4 and DR5 are undefined. Then we'll come to DR6 and DR7. DR6 and DR7 are two important debug registers that play a very important role in the debug register process. We'll see one by one the bits that are defined in DR6. I'll just give the introduction. In DR6, the first bit is B0, then B1, B2 and B3. They are nothing but breakpoints. And BD, BS and BT, they are again nothing but breakpoints that help us to define the different tasks. Like BD is for the break for debug register access. BS is for the break for single step. BT is nothing but break for task switch. So the different functionalities are provided by these bits. Then DR7 will consist of again different type of bits. First one is L0, G0, L1, G1, L2, G2, L3, G3, LE, GE. Now L means nothing but wherever L is there, it is nothing but local, and wherever you can see the letter G, it is indicating global. Fine. And we can say E means what over here, LE means what over here, local enable, and GE means what over here, global enable. Okay. Then we will come to the next bit, that is the GD bit. It is nothing but global debug access. It is giving you the global debug access. And then come to the last part, RW. Wherever you all see RW, that is R0, R1, R2 and R3. It is indicating the read write access. And wherever you see LEN, that is len 0, len 1, len 2 and len 3, it is indicating the breakpoint length. Okay. So debug register is a 32-bit debug register consisting of DR0 to DR7. That means total 8 debug registers are present, out of which DR0 to DR3 is having linear address for different breakpoints. That breakpoints are from 0 to 3. There are total 4 breakpoints. Then DR4 and DR5 are undefined. DR6 consists of various number of bits. Also DR7 consists of various number of bits. So we will see this DR6 and DR7 in detail. Now I'll just read out the point. The debug registers 0 to 3. Okay. The first 4 debug registers, that is DR0 to DR3, they hold the 4 linear addresses for the breakpoints. Okay, so what do you mean by a breakpoint? A breakpoint is nothing but it is an intentionally stopping or pausing place in a program. Means you are intentionally stopping the execution or intentionally stopping the flow of a program in a particular place, that is you're running a breakpoint. So for what? To put in place for a debugging process. Now breakpoint is nothing but same like a speed breaker. When you are walking on a road, there are speed breakers. So why those speed breakers are put intentionally, so that the person should go drive the vehicle slowly. He should not go in a speed in order to avoid accidents. So the speed breakers are put in the road. Similar is the task of a breakpoint over here, but what it is doing, we are intentionally putting or stopping or pausing a program. In We are putting a breakpoint in a place in a program. Okay, so put in place for a debugging process, but nothing for a debugging process. You are adding a breakpoint so that you can perform a debugging process up to that particular defined breakpoint position. Fine. Then the next is addresses in these registers are compared with the address of each instruction. Whatever is the address in these given registers, they are compared with the address of each instruction at the time of instruction execution. Okay, and if a match is found, then an exception one, that is debug default, is generated. Now what is the meaning of this sentence? See, the registers, they contain addresses. Okay, and when these addresses are contained in this register, parallelly when you are executing each instruction, similarly when each instruction is getting executed, the address of that each instruction at the time of its execution, it is getting matched or it is getting compared. While you are doing comparison of the addresses with of the instruction with the address present in the register, and if you find a match, then it will produce a exception one. Exception one means what? A debug fault is generated. If two same addresses are found, then exception one, that is the debug fault, is generated. So this will allow your 80386 microprocessor to monitor up to the 4 different addresses in the system. Why 4 different addresses in the system? Because you are having 4 types of linear addresses. Okay. Then DR6, that is debug register 4 and debug register 5, sorry, they are, these registers are undefined. Okay, they are not into use. Then we'll come to DR6 and DR7. They indicate the status of the processor at the breakpoint addresses. Whatever will be the status of the register, or whatever will be the status of the processor at the particular given breakpoint, it will indicate the status of that given processor. Okay, now the status bits. Now we will see the status bits. See, these are called as status bits. See, in the DR6, all these bits are called as the status bits. So we'll see one by one. B0, that is the breakpoint 0. 80386, the 80386 sets this bit when it refers the linear address contained in the DR0. When will be your breakpoint 0? If this bit is set, no, B0 bit, if it is set, then it will refer the address that is contained in the DR0 because it is B0. So it will refer D0 according to the conditions that are set by the len 0 means length 0, RW0 means read write access 0, L0 means local enable, G0 means global enable, LE means local exact, and GE means global exact fields in the DR7. So a key point that I'll tell you to remember in this is the B0 breakpoint. Whenever this bit is set, it will refer the linear address that is contained in the DR0. Okay, fine. B0 will refer the address that is contained in the DR0. But according to the conditions, whatever will be the conditions that are set, and wherever you find this 0, length 0, read write 0, L0, G0, length enable, G enable fields in the DR7. So just see over here, the B0 breakpoint, when this bit is set, set means what? Set to 1. It will refer the linear address, this linear breakpoint address from DR0. As this is 0, it will refer DR0 and breakpoint 0. Okay. And this bit will refer the DR0 register only on the conditions that are set by the DR7 register, but in the DR7 register it will refer to which conditions, the conditions that are set. Now everything that is 0, see, length 0, sorry, L0, G0, then we'll go to LE enable, GE enable, then we'll go to read write 0, length 0. Whatever is 0, B0 will refer to DR0, breakpoint 0 with due respect to the conditions of L0, G0, then LEGE and length and read write 0. Whatever is 0, refer to that. Similar is the condition with breakpoint 1 and 3. See, B1 to B3. These bits are similar to B0, means what? When breakpoint 1 is set, it will refer to the linear address contained in the DR. See, whenever the breakpoint 1 is set, it will refer to the linear address that is contained in the DR1 register. Because it is breakpoint 1, it will refer to debug register 1, and similarly from debug register 1 it will refer to breakpoint 1. Okay, and this bit is set, but depending on the conditions from the DR7, L1, G1, then read write 1 and len, that is len len 1. Okay, similarly when your B2 is set, it will refer to DR2 breakpoint 2, but depending on the conditions from len 7, G2, GL2, then length enable and read write enable. Similarly for B3 will be the case. Okay, so it is given over here. Breakpoint 1 and 3, these bits are similar to B0. In each case, the linear address is referred from the respective debug registers. For example, B2 will refer D2, B3 will refer D3, B4 will refer D4. Okay. So now next bit we will come, that is the BD bit in the DR6 registers, that is break for the debug register access. So the access for the debug registers can be locked. You are having, or there is a certain mechanism that you can lock the access to the debug registers. But how? With the help of, by setting the GD bit in the DR7. So break for debug register access, this bit will, what it will do, the access for the debug registers can be locked by setting the GD bit. GD bit is doing your global debug access, okay, in the DR7. So the BD bit, if set, allows to invoke the exception 1 handler. Exception 1 handler means what? Your debug fault. If processor tries to access the debug register, even though the access is locked. I'll read again, I repeat again. BD bit, that is the break for the debug register access. The access for the debug registers can be locked by setting the GD bit in the DR7. If the BD bit is set to 1, or if the BD bit is set, then it allows to invoke exception 1 handler. If processor tries to access the debug register, even though the access is locked. This means what? If processor, it will try to access the debug register even though the access is locked, means you are denying access, and even if the processor tries to access that debug register, then exception 1 handler will be invoked, or it will be called. Then next is the break for single step. This bit is set if the 80386 has invoked exception 1. Since trace bit is set. Since trace bit is set means what? Your TF bit. Okay. the TF bit is set in the trap flag is set in the in the flag register. This is just doing your, it is adding a break for a single step. Whenever a single step is there, it will add a break. Then again single step, it will add a break. So only it is said that this bit, when the BS bit is set, if the 80386 has invoked exception 1, exception 1 means what? The debug fault, since trace bit is set, and it needs to trace whether you are performing the execution properly. And when is this possible? When your trap flag in the E flag register is set. Now, what is the functionality of the trap flag that we had seen in the flag register? That is, the trap flag, it is generated after execution of each instruction. Whenever each instruction is executed, the trap flag bit is set. Okay. Then next is the BT, break for the task switch. When a task is initiated whose trace bit is set, the 80386 invokes an exception 1 if BT bit is set. BT means what? Task switch. You are just switching the task. Whenever you want to switch a task, then this bit is set. When a task is initiated, let that task be anything whose trace bit is set. Trace bit means what? Again, you are what do you say? You are setting a trace bit in order to trace or track the event or track the flow. Then the 80386, it will invoke exception 1 handler if the BT bit is set to 1. Okay, just keep in mind, when BT bit is set to 1, exception 1 is invoked. Then we'll come to the next debug register, that is the DR7. It controls the debug features. Whatever are the debugging features, they are controlled by your DR7. By programming bits in this register, programmer can configure the debug operation of the 4 linear address breakpoints. Whatever breakpoints you are applying into your program, who is handling these breakpoints? DR7. Okay, because it will be, these breakpoints will be handled depending on the conditions of the various bits that are set in your DR7. So each breakpoint is controlled by a set of 4 fields. Now what are these 4 fields? See these 4 fields: L0, G0, L1, G1, L2, G2, L3, G3. Okay, so this is 1, 0, 1, 2, 3, and 4. These 4 fields. Fine. So what are these fields? Local enable. When this bit is set, the breakpoint address in the DR0 is monitored. Okay, as it is 0, so which it will refer to the which register? DR0. Okay, and what it is doing, see, it is the address, the breakpoint address in the DR0 is monitored as long as 80386 is executing the current task. When a task switch occurs, this bit is cleared by 80386 and it must be re-enabled by writing into the DR7 required. Now, local enable, it is nothing but whenever you set this bit to 1, then the breakpoint address in your DR0 register, it will monitor, it will start monitoring, or it is monitored. Until what time it is monitored? As long as it is executing the current task. Whatever is the current task, let that current completely, whenever it, until it is getting completely executed, the DR0 will get monitored. Okay, and once this execution of the current task is completed, then there will be a task switch. After completion of one task, it will switch to another task. Then there will be a task switch. Okay, so when a task switch occurs, then this bit, which bit? The L0. See, this L0 bit, it is cleared. It is cleared means it is reset. Okay, it is reset to 0 by the microprocessor. And when once it is cleared by the microprocessor, it must be again re-enabled. Means again it should be re-enabled by writing its position back into the DR7 register, because where is L0, that is local enables position in the DR7 register. So whenever after you are always clearing this bit, it should be re-enabled by writing in the DR7 register. Then is the global enable. Now what is this global enable doing? When this bit is set, the breakpoint address in the DR0 is monitored all times regardless of the task. This bit must be cleared by writing into the DR7. Local, meaning of local means what? Monitoring the task only for that particular, monitoring the execution of the task only for that particular task. But when you come to the word global, means you have to monitor the DR0 register for all the time, throughout the time, regardless of the task. Let that task get over, then it will come to the second task, then even after the second task execution is over, it will come to the third task. What is the meaning of global? It will monitor your DR0 register for all the time regardless of the task, and once this bit is cleared, it must be re-enabled again by writing it into the DR7 register. Then we'll come to read write access. Okay, this bit decides the type of access that must occur at the address in the DR0. Means it, what it will do, it will just decide the type of access, whether the access provided is for writing or whether the access provided is for reading. Then we'll come to len 0. Len 0 means what? It is the breakpoint length. The breakpoints are further distinguished by its size. Actually no, there are breakpoints, and these breakpoints, they are distinguished by their sizes. Okay, so each address register from DR0 to DR3 also has a associated length, that is depending on the size of the breakpoint, they are associated with their length fields. Okay, and that length field specifies the length of the data item being monitored, or depending on the size of the breakpoint, the length is associated, and depending on the length field, then that that much length of data item will be monitored. Okay, so there are in all four lengths such as L, G, R, W, and length for four breakpoints from B0 to B3 that I showed you in the diagram itself. So the DR7 contains three more bits. What are those three more bits? Now we have seen L, G, that is local global, RW, that is read write, and len means length. Then more three bits are LE, GE, and GD, that is local exact, global exact, and global debug access. What does this LE do? The pipelined architecture of 80386, it will fetch, fetches, decodes the next instruction before the current one is completed. What is the meaning of pipeline? Before the first, see now one first instruction is getting executed. Okay, before the completion of the first instruction, what does the pipeline do? It will start fetching and decoding the next instruction that is to be executed before the completion of the first current instruction. So that is the meaning of pipeline. So due to this, 80386 may not set status bit in the DR6 at the instant breakpoint occurs. So when this is happening, what the because of this process, the 80386 microprocessor they may not set the status bit in the DR6 register. Why they may not set? Due to the or at the instant breakpoint occur. If there is a instant breakpoint occurred, then it will fail to update the status bit. So if you set the local exact bit, 80386 sets the corresponding status bit at the same instant at which breakpoint occurs. So what is the meaning? What does this LE do? Local exact do? Even though if you fail to set the status bit in the DR6 register, and if you set this LE bit, then the microprocessor, what it will do? It will set the status bit corresponding, it will set the corresponding status bit at the same instant at which the breakpoint was occurred. Suppose the breakpoint is occurred at line number 4, then the 80386 microprocessor, what it will do, it will set the corresponding status bit at that same instant only. Okay, then when 80386 is running the current task, after that when a task switch occurs, this bit is cleared and this bit applies to all the 4 linear breakpoints. LE, that is local exact, is applicable to all the 4 breakpoints, because the work of this bit is that if the status bit in the DR6 is failed, is not, we cannot say failed if we don't set the status bit in the DR6 register, then this status bit setting work is done by this LE bit. Okay, and it will be understood that there is the instant breakpoint is occurring, so it will give the corresponding status bit to the processor. Then is the global exact. This bit is similar to LE. If the bit is set, 80386 informs about the breakpoint at the instant it occurs regardless of the task. Now local exact is set for only that particular task, but global exact is set for all the tasks regardless of the task. So means what? This bit will be applicable for all the 4 breakpoints at that instant regardless of the task. That means globally it will work. And what is GD? Global debug access. When this bit is set, the processor denies the further access to any of the debug register. See, global debug register is such a bit that is that if you set this bit, then the access will be denied to any of the debug register. Let it be either reading or writing. So it will not allow access to any debug registers unless if you want to uh, have access to read or write to the debug register, then you will have to set this bit, or you have to clear this bit. Not set, sorry, you will have to clear this bit. Then is the test registers. There are test registers that are TR6 and TR7. This test registers of 0 to 31, that is 32 bit. So among the 8 test registers, DR0 to DR7, only 2 test registers are currently defined. This means what? DR0 to DR7, they are not defined, and currently which test registers are defined? TR6 and TR7 are defined. So this is the figure of the test register. TR6 is having bit C, W dash W, U dash U, D dash D and V, and next is the linear address. And TR7 is nothing but the having various bits as REP, HT, sorry, TH or HT we can say, and physical address. Now there is one just one we can say about the test registers, that the test registers are there, they are not a standard part of 80386 architecture. Why they are not standard part? Because they are provided solely to enable the confidence of testing. They are just solely, they are we can say they are played or provided individually to enable the confidence of testing of the TLB. Now there is a word across, when you will come across this test register, that is TLB. TLB is nothing but translation look aside buffer. I will tell you further when we come to that point. So TR6 is called as the test control register, as it gives the control for the test operation. Okay, and TR7 is called as the status register, test status register, as it provides the status of the corresponding test. See, 6 is nothing but giving you the control that you can test the operation, and TR7 is giving you the status. Means what? It is telling you what is the current status of the test operation. So they are used, so this test registers, they are basically used to test the TLB. See, what is TLB? Translation look aside buffer. Now the TLBs are used with the paging mechanism. Paging means what? They provide page table entries, page directories, etc. Whatever is the paging mechanism, they are provided by the TLB. Now TLB is nothing but It is used for the translation of linear address to the physical address. I will just tell you in short what is TLB. It is a high speed cache, but it very high speed cache. Why it is called as a high speed cache? Because it is set up for the page table entries, and the TLB will first check if the page, we can also say if the page is already in the main memory. It will check whether the provided page, is that provided page already present in the main memory. Okay, if it is not in the main memory, a page fault is issued. If you don't find entry of that particular page in the main memory, then at that time a page fault is issued. Then the TLB is updated to include the new page entry. Very easy. Whatever the page table that you are searching, if it will, the translation look aside buffer, it will search, suppose page number 2, then page it will search for page number 2 in the buffer. If that page is not found in the main memory, it will generate a page fault. And after it generates a page fault, what it will do, it will include, after how this issue will be resolved, it will include page number 2 in the main memory. Okay, so we can say that they are nothing but a cache, high speed cache, just keep in mind, and it is used for translation of linear address to physical address. That's it. Then I hope you understood TLB. Now we'll move further. The different bits of the test registers are explained below. Linear address, it holds the tag field of the TLB. See, it is a buffer. TLB means what? Actually, it is a buffer. And this TLB consists of two parts. One is tag field and another is the data field. This tag field is actually, what do you say? It is just 24 bit wide. It is nothing but having a size of 24 bit, and it contains, this tag field basically will contain 20 upper bits of linear address. Whatever will be the upper bit linear address, it will be contained by your tag field, and a valid bit and a 3 attribute bits. What the tag field will contain? 20 upper bits of linear address, a valid bit, and 3 attribute bits. That this is nothing but a combination of tag field. As the linear address, it is, as the TLB is consisting of two fields, that is tag field and data field. So tag field will be associated with your attribute bit, valid bit, and linear address, upper bit linear address. And the data bit or the data portion, it will consist of higher 20 bits of the physical address. So just simply keep in mind, tag field will be nothing but indicating your linear address, and data field will be indicating your physical address. But in the data field, there will be only physical address present, whereas in your tag field, in this tag field, it will contain linear address, valid bit, and 3 attribute bits. Okay, so the linear address, it will hold the tag field of the TLB. Physical address, it will hold the physical address of the TLB. Now what does this V stand for? See, now we'll see these bits: V, D, U, and W. See, V will indicate if the entry in the TLB is valid or not. Whatever the entry is made in the translation look-aside buffer, is that entry valid or not? It will be checked by this bit. What does this D indicate? It indicates if the entry in the TLB is not directly, dirty. Dirty means what? It is not updated in the next level of memory. It should be updated, just updated. Whatever is the entry made, it should not be dirty. Dirty means what? Old data. And uh, in short, it is not updated. Okay, why it should be updated? If the entry is updated, then and then only it can go to the next level of memory. If the entry is not updated, then it cannot go to the next level, higher level of memory. U means what? This bit is assigned to the TLB. U indicates user. Is U means what? User. And wherever there is a dash, see, it is not, this indicates dirty, not dirty, user, not user. Okay, we will just have a sole bit, it will not have a dash because it is checking the valid entries. And what does W mean? This bit indicates if the area addressed by the TLB entry is writable or not. If it is W, means it is writable. If it is W dash, if it is W dash, it means it is not writable. C means what? C will selects between the write and look up for the TLB. It will just do the selection process between write and look up of the TLBs. TL bit. If this bit is set to 1, it indicates the TLB hit. Hit means what? That it is actually hitting to the translation look aside buffer. REP instruction means what? It will select which book of the TLB is written. Selects which block, sorry, not book, I repeat, selects which block of TLB is written. Written means you're actually writing. Here I want to make one correction, or I can say just one point I want to bring into consideration. This PL bit, see over here, this PL bit, in some places, this PL bit is written as TH bit. Okay, so I request everyone either TH or PL. Fine, these both are okay, but preferably write over here PL. This diagram, I I just want to make correction over here. In this bit, you should just mention over here PL. Then the next is the system instructions. There are some instructions that deal with functions. They are given below. Just this is for your reading process. First is the verification of pointer parameter. Then is the addressing descriptor table. Then is the multitasking. Then is the co-processing and multiprocessing. Input output, interrupt control, debugging, TLB testing, and system control. Uh, Over here, I want to just tell one part of the test register. The test registers, no, they can either be a source operand or they can either be a destination operand, and they are usually used to do a self test. So we can say that they are actually just for the testing purpose and no other purpose. They are just not a part of your 80386 architecture, but they are individually or solely enabled to boosting the confidence of the testing purpose. So you can read these instructions, and if any doubts, you can feel free to contact. So thank you.